Hello and welcome to the January session of GeoStudio Tech Talk. These monthly webinars are designed to improve our understanding of the software and ultimately promote success in your engineering projects. This month's Tech Talk will introduce the soft soil model, which was recently implemented in SigmaW. A recording of the webinar will be available so that participants can review the demonstration afterwards. My name is Curtis Kellen. I'm the Director of Research for GeoStudio. Today's webinar will be approximately 30 minutes long. Attendees can ask questions via the chat feature, and I will respond to those questions by email as quickly as possible. GeoStudio was developed for geotechnical engineers and earth scientists. As such, it comprises a range of products that can be used independently or together to solve a wide array of problems. Today's webinar will focus on Sigma. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoSlope website. Here you can find examples with detailed explanations, tutorial videos, the reference books, GeoStudio add-ins, and our previous webinars and online learning materials. In today's webinar, we will begin by reviewing the theory of the soft soil constitutive model. Then, a step-by-step procedure will be presented for parameterizing the soft soil model, and simulations will be verified using the measured and laboratory results. A demonstration of the steps for modeling a field scale example using the soft soil model will also be provided at the end of the webinar, and then finally some concluding remarks will be reviewed. The soft soil model was primarily developed for simulating the response of highly compressive soils, such as normally consolidated clays and clayey silts. This constitutive model is formulated within the generalized elastic plastic framework and takes advantage of some of the features of modified CAM clay. As a first comparison between the soft soil and modified CAM clay models, let's consider an isotropic loading state. The modified CAM clay model assumes a linear response in the specific volume, mean confining stress, natural log of mean confining stress space. In this model, the compression indices for normal compression and overconsolidation are represented by the Greek letters lambda and kappa, respectively. In a similar way, the isotropic elastic and elastic plastic responses are assumed to be linear in the soft soil model. The volumetric strain, however, is considered to be the vertical axis in this model. And in the natural log x-axis, the mean effective stress is additive on the cohesion times the cotan of the friction angle. Since the coordinate space in the soft soil model is not identical to that of modified CAM clay, the compression indices are called modified compression index and modified swelling index. The asterisk on lambda and kappa are used to signify or distinguish the difference between soft soil and the original modified CAM clay indices. Before going into the demonstration on parameterization, it's helpful to consider some other aspects of the soft soil model. First, the soft soil material model is a critical state-based constitutive model, so different stress paths eventually tend towards a failure line, shown here in QP space. The failure criteria adopted by the soft soil model is that of the Mohr-Coulomb failure law, at least in triaxial stress space. Shown here is the equation for the Moore Coulomb failure line, F, is equal to mx plus b. And so in this case, the slope, m, is related to the friction angle by this leading relationship. X is our x-axis, p plus c cotan of the friction angle, and the intercept is q. Now note that if you access our reference book for static stress strain modeling, you will discover that the soft soil model actually uses a slightly more advanced constitutive law, which is load angle dependent. However, it simplifies to this simple expression of what you would call mu, the Greek letter mu, in triaxial space. The cap on the soft soil model is an ellipse with a horizontal major axis. And the aspect ratio of this ellipse is controlled by a stress ratio called m, also the Greek letter mu. This stress ratio is not independent of other material parameters and can be calculated based on those input parameters. We see in this relationship that it's somewhat awkward, but in it we recognize the coefficient of earth pressure for the normally compressed state, and that is of course at rest. We also see the two modified indices referred to on the previous slide, and also in this relationship is Poisson's ratio, nu prime. Now for a stress ratio that is, or I should say a stress path that's tracking inside of this yield locus and never intersecting Moore Coulomb or the cap yield surface, the strain increments volumetrically and deviatorically, subscript V and Q, in the elastic range are linked to changes or increments in mean effective stress and deviatoric stress by this compliance matrix. We can see that it's diagonal and that the off-diagonal terms are 0. In the 1-1 position of the matrix is 1 over the bulk modulus of the soil, K sub S, and in the other diagonal term, position 2, is 3 times the shear modulus. Now the soft soil model makes an assumption about the nonlinearity of the elasticity. And so if we unpack these two relationships, we see that the moduli, the elastic moduli, are of course linked to the swelling index, which is a purely elastic property, and also to the confining stress, the x-axis in the QP space. Also, and as always, Poisson's ratio is a fundamental part to defining elasticity. If a stress path engages the cap yield surface, then the cap will expand, its size given by its tip stress, P sub P, and eventually the stress path will intersect the Moore Coulomb failure line. Prior to intersecting the Moore Coulomb failure line, the plastic volumetric and deviatoric strain increments, you see the superscript P now, are linked to increments in P and Q by a new compliance matrix shown here. Now for those of you that are interested in the details of this formulation, for generalized stress space, I again refer you to the reference book for static stress strain modeling, but it's helpful to look at this simplified triaxial condition to see that we now require the difference between the two indices, shown 2 slides ago. We also now require a stress ratio, eta, which is this subscript C on here, and you can see that as opposed to being Q over P, we have to include c cotan phi, which is this offset distance in QP space. And that stress ratio, eta, will control the elastic plastic response, or excuse me, again, the plastic strains, because its relative location to m, that aspect ratio. And so just like this equation was a classical equation of a line, mx plus b, the equation that describes the cap is a classical equation for an ellipse. So in light of those previous few slides, that very brief overview of the theory of the soft soil model, we can now summarize that the constitutive model requires 3 stiffness constants. Those are the modified compression and swelling indices, and of course Poisson's ratio. Then we need the strength constants, including an effective cohesion and an effective friction angle, in order to shape the ellipse of the cap. We also needed the coefficient of lateral earth pressure at rest for the normally compressed state. These constants determine the soil type based on the soft soil model. Some other parameters will also be needed to describe the initial conditions of a specific soil sample. These include the initial void ratio, the unit weight of the soil, and the overconsolidation ratio. We can now discuss a step-by-step parameterization procedure for determining the soft soil model constants from a number of drained triaxial tests. Step 1 involves determination of the effective friction angle and effective cohesion. The failure states from numerous triaxial tests at different confining pressures are theoretically located on the Mohr-Coulomb failure line in QP space. As such, the slope tan beta, as well as the y-intercept alpha, can be calculated using the method of least squares, shown here, where n is the number of data points. In this case, we can track these endpoints onto the failure line, and we will see that there are 4 in total. And so these expressions for the least squares fit. They're a bit cumbersome, but you can imagine easily doing this in a spreadsheet. You can see, for example, that this term requires summation of the P and Q at failure minus the summation of the P's times the summation of the Q's at failure, and so on. Now, in both cases, these values can more easily be obtained in spreadsheet programs like Excel by using the trendline functionality. So it will do it on your behalf, but if you wish to also program it in a spreadsheet, we'll be showing these least squares formulas throughout this presentation. Now with that done, the effective friction angle and the effective cohesion can be found by changing the coordinate space back to a shear normal stress space. Now that requires some mathematical gymnastics, and so for all intents and purposes, all we need to know is that once we have beta and alpha, we simply apply these formulas to get our two strength constants. The second step of the calibration procedure is to determine the effective Poisson's ratio. Poisson's ratio is defined as the ratio of the change in the element's radial strain to the change in its axial strain. It's important to remember that Poisson's ratio is a purely elastic constant, and so the branch of our test that we use to obtain Poisson's ratio has to be from either a reloading branch or an unloading reloading branch. So the least squared formula then applied to what is shown here as 6 data points would look like this. we simply have to sum the accumulated axial and radial strains multiplied together, and then divide that by the summation of the square of the accumulated axial strains at our 6 data points. And that would be a trend line passing through these points. Notice the negative sign here, because for every positive compression, there is a radial expansion, and so hence the positive axis is pointing up, but we're in the negative accumulated radial strain range, so the slope of this line, of course, is negative. But Poisson's ratio is always written and assumed to be a positive constant. The third step is to determine the modified swelling index, or the slope of the overconsolidation line. The trends of the measured values of P prime and the accumulated volumetric strain, epsilon subscript v, in the overconsolidated portion of the graph can be fit by a straight line. I do want to emphasize again that, like Poisson's ratio, kappa star is a purely elastic property, and therefore the test data used to acquire it must be in the elastic range. The slope of this line is calculated directly using the method of least squares. You can see here that that formula requires an intercept, which is denoted with the superscript not 0, and then it is also designated as overconsolidation, and you'll see why in just a moment. So this is located at some value, that intercept of some value of our confining stress, which includes that cohesive component, that offset. And so you'll see here that in this formula is this other term called x, lowercase x, subscript OC for overconsolidation. And it is in here that we need to lock into a specific value of mean effective stress at which that intercept is taken. That is normally 1 kilopascal, but it does not have to be. Now, an alternative method for estimating the constant, kappa star, is to use the corresponding parameters measured during an unload-reload step. For a normally consolidated stall, this unloading-reloading process is required for estimating the kappa star value. So the method of least squares can once again be applied to this straight line. The only difference between these two formulas is the intercept. You can see now that we had OC, but now we have UR to indicate that the data is on an unload-reload line. And UR again must lock into a specific value of mean effective stress where the intercept is taken. And again, that would be 1 kPa. So I just want to point out here that what you are seeing, the reason this blue line exists right here, is you can imagine a scenario in which the specimen is prepared in the triaxial chamber. It is isotropically compressed to, say, this point right here, where it is then sheared in triaxial compression. And if it yields immediately, then it would track along this line, and it's at this point where unloading might occur along the kappa line. The fourth step of the calibration procedure is to determine the modified compression index, or the slope of the normal compression line, lambda star. The slope of the normal compression line corresponds only to an isotropic loading condition. In other words, if we had taken that previous example that I just walked through, let's say that the specimen was isotropically compressed along the overconsolidation line, and then it yields in isotropic compression, and we track along the normal compression line. Hence, it is often referred to as the isotropic normal compression line and designated ISO-NCL. But anyways, if we did that, we tracked down this line and then we unloaded, we would be on the unloading-reloading line. However, as I just illustrated on the previous slide, it's often the case where a specimen is isotropically compressed to some point prior to yielding in isotropic compression, at which point we track along here in the volume plane. And so this blue line comprises both plastic strains and elastic strains. The elastic strains are revealed by an unloading loop. So for example, if we continued with triaxial shear up to this point right here, there would be a magnitude of total volumetric strain comprising both elastic and plastic. That would be the vertical distance between this point and this point. But if we unload back to the confining stress that is just under here, then this portion, this short portion right here, short length, would be the recoverable elastic strains, and the remaining portion would be the irrecoverable plastic strains. Those are the strains we need in order to get the compression index, because that is characterizes the plastic straining of the soil specimen. So if we had this isotropic data shown here on the left, this would be an easy exercise and would look identical to that shown on the previous slide for obtaining kappa star. But if we have the data on the right, the process is just a little bit more involved. So to deal with this issue, what we can do is we can transfer the measured results into another stress space, or I should call it volume plane, in which the sample response is linear, even on the what we've referred to here as plastic line. So you'll notice that the x and y axes in the space are functions of the measured parameters, the accumulated volumetric strain, which is right here, and then P and Q, of course, are stress and variance, and then the constants phi prime, the friction, effective friction, the C prime, effective cohesion, and our swelling or modified swelling index, kappa star. So y versus x, you can see that on the y-axis, we're essentially taking the accumulated volumetric strain, which is both elastic and plastic, that vertical section of line that I pointed out earlier, and we are subtracting off the elastic component, leaving us then with the plastic volumetric strain. In this axis, we have the natural log of our confining stress variable multiplied by the aspect ratio squared plus the stress ratio eta squared. So fairly simple operation. And the slope of this new line in this coordinate space is the difference between the two indices. And again, I think I highlighted that here. So the least squares method can be used as before, where again we have n number of data points and our new y and x data points, not shown here as individual points, but you can imagine them. There's one problem, however, and that is on this axis, we require knowledge of the ratio m. And so m, if we recall, was also a function of our modified indice, lambda star. So in order to overcome this difficulty, we have to guess at lambda star, calculate m, then this new space that we've plotted would be formed, if you will, before our eyes. You can imagine in a spreadsheet. We could do the least squares, get gamma star, and now we have to iterate. And so we would update m, which would update our plot, which would update lambda star. This iterative process is generally repeated a handful of times until both mu and our index stops changing. We'll demonstrate this in just a few slides. Now, the fifth step of the calibration procedure is to calculate the overconsolidation ratio for each soil sample. To do this, it is required to recognize the mean effective pressure at which the response of a soil specimen transitions from being elastic and overconsolidated to being normally compressed. And we'll call this the yield pressure, gamma Y, shown here by this arrow. Switch to a laser pointer. There's the arrow right there. The OCR, the overconsolidation ratio, is actually defined as the ratio between the isotropic pre-consolidation pressure, P sub P, and the initial isotropic pressure, P prime naught. As stated earlier, the response of the specimen changes from elastic and overconsolidated to elastic plastic and therefore normally compressed only if the stress path touches the yield surface. As a result, for a stress path that is not necessarily isotropic, the yield pressure gamma prime Y is less than the isotropic pre-consolidation pressure P subscript P. These two pressures, however, are not independent. For example, in a 3-to-1 drain triaxial stress path, the deviatoric stress at yield is 3 times the difference between the yield and the initial pressures. So the isotropic pre-consolidation pressure, P sub P, can be expressed in terms of yield stresses using the yield function. In other words, we've taken the yield function shown previously and we've solved for this tip stress, P for an ellipse that passes through the deviatoric and mean effective stress at yield. And so the isotropic pre-consolidation pressure is determined, and finally we get the OCR as that ratio of P sub P and P sub naught. So now, as an application of the step-by-step parameterization procedure, let us consider 3 triaxial compression tests on a clay that was conducted by McGinty in 2006. You can see here that we have 3 confining pressures, 58, 94, and 150 kilopascals. The effective friction angle and the cohesion of the soil are calculated on the first step of our parameterization procedure. The deviatoric compression stresses in these triaxial tests continued until failure was achieved. The failure state of each test can be represented as a single point in QP space. And then a failure line can be passed through these points, and the slope and intercept can be determined using a trend line or the least squares formulas presented earlier. In this case, we see that M, our slope, is tan beta, and that's 1.353, and the intercept is a negligible but non-zero deviatoric stress of 1.455. And so when we transform that into our shear normal space with which we are accustomed, we can take tan beta and alpha and convert that using the formula shown previously to an effective friction angle and effective cohesion of 33.5 degrees and 0.712 kilopascals. The second step was the determination of Poisson's ratio. And so in this plot right here, we are showing the axial versus radial strains. And the sample response you can see is almost linear before the yield surface was engaged, as marked by the symbol X. And so it's the data prior to the X's that must be used to determine the elastic effective Poisson's ratio. And so in this case, we can see here that the slopes are all pretty well equal. And in fact, an average Poisson's ratio is obtained as 0.353, which is a very common value for soft clays. The third calibration step can also be applied to the triaxial test data mentioned previously, that is, the overconsolidation branch in each of the three curves, except now we're looking at our volumetric and confining stress plane. And so you can see here that the entire path is presented, but we've isolated just the elastic data in all three cases. We've used the trendline capability in Excel to fit three trend lines through those data, and you can see here that we can pull out our slopes, which is our modified swelling index, 0.033, 35, 37, giving us an average of 0.035. The modified compression index, lambda star, is calculated on the fourth step. In the proposed coordinate space, the triaxial compression branch in each of the three curves is projected to a straight line. The average slope of these lines, which represents the difference between the compression and swelling indices, is about 0.141. This results in a modified compression index of 0.176, given our previous value for kappa star, and a yield surface aspect ratio, which we obtained through the iterative procedure, of m equal to 1.904. And as mentioned, since that iterative procedure is a back and forth between obtaining lambda star, updating m, updating our data in our transformed space, and back and forth, we here show a graph of that iterative procedure. It's worth noting that what we've shown here is that our first guesses for lambda star could range from kappa star to say 20 times kappa star, and that is what these three lines actually are. But you can see here that even with these large disparity between the initial guesses, it still only takes 3 iterations before the values converge. The fifth step is to determine the overconsolidation ratio of all three specimens. So first of all, the yield points of the samples are detected. The yield values P prime sub y for tests A1, 2, and 3 are about 84, 106, and 174 kilopascals respectively. According to these yield pressures, 3 deviatoric yield stresses are calculated from the 3-to-1 stress path, and the isotropic preconsolidation pressures for each sample can then be calculated from the yield function as 104, 109, and 182 kilopascals respectively. This then, writing the P prime P over P prime sub y, gives us our isotropic overconsolidation ratio, which you can see here for each unique sample was 1.8, 1.2, and 1.2. The results of the calibration procedure for the clay can be summarized as follows. 3 stiffness constants, including lambda star, kappa star, and the effective Poisson's ratio. The Mohr-Coulomb strength parameters, including the effective cohesion and friction angle. And the sample-specific parameters for the 3 tests. So we show one screen capture, but of course each of the 3 specimens have their own unique values for E0 and OCR. The different simulation results of test A1 are compared here with the corresponding laboratory results. Discrete data points are laboratory results, and the continuous black lines are the result of the sigma simulations. The analytical results of the soft soil model are also shown in the three diagrams as orange dashed lines. The full compatibility of analytical and numerical curves shows the reliability of the implementation process of this particular model in Sigma. In addition, the acceptable consistency between the lab results and the constitutive model simulations indicates the capabilities of the calibrated soft soil model in predicting the response of a soft clay. The same trends can also be observed for the second test. You can see here that the lab data was either not well captured by our parameterization, and that maybe yield actually occurred at a slightly higher confining pressure. However, that observation is somewhat contradicted by the apparent well-predicted yield stress in these planes. So the alternative explanation, and maybe it's a combination of the two, is that there was a seeding problem with this particular lab test because the volumetric strain is suspiciously low over a fairly large axial strain range. Again, not exactly sure. Overall, the data seems to be well predicted or fit by our numerical simulations. And we'll see that that same trend continues in the third set of tests. And so that brings us now to our field scale application of the soft soil model. The model, which is the project file referred to as submerged construction of an excavation, involves the simulation of the stage construction of a submerged excavation supported by a diaphragm wall and pre-stressed strut. The elevation of the water table inside the excavation is assumed constant and commensurate with the initial water table. The geology comprises 20 meters of soft clay, represented of course by the soft soil model, overlying a sand, which is represented here by the hardening soil model. The water level is 2 meters below the ground surface. And here is the analysis tree that you'll see in the project file, in which we have our in situ stresses activated via the K-NOD procedure. Then we have 5 additional phases involving, in this case, a surcharge load at the ground surface, then the first excavation, then the activation of the strut, then the second excavation, this region right here, followed by the third excavation. And you maybe saw as the animation progressed that a hydrostatic boundary condition is being applied to the new exposed ground surface after each subsequent excavation phase in order to put the water back. So in other words, Sigma by default removes all material, the total stresses, from an excavation. And so we have to, since it is submerged in water, always at 2 meters below original ground, we have to put that water back via a hydrostatic pressure boundary condition. And so I'll let you explore exactly how that was done. It is quite intuitive. You can explore that in the actual project file on our website. In the next few slides, I just want to very quickly examine some of the things you can explore in these types of simulations. The first is the stress distribution of vertical total stress as a result of submerged excavation. And so this is a plot along the center line right here, showing those total stress profiles at all phases. There's some overlap in this figure. And so we can see here that at the final level of the excavation, the final level of excavation, the third excavation, that the Y total stress at the base of the excavation, right where my laser pointer is at around 180 kilopascals, which would be equal to the hydrostatic pressure calculated by taking the 18 meters of water that remains and multiplying by about 10 kPa per meter. The horizontal displacements of the model at the end of the construction are presented here. So again, this is horizontal or X displacement. A review of the wall deflection patterns via draw graph reveals that the strut installation, this yellow plot right here, had a rather significant effect on the displacement pattern and magnitudes. In addition, the maximum deflection of the wall is at about 22, this after the second excavation, 22 millimeters, and then finally 62 millimeters at the end. And so the deformed mesh of the model, as well as the X displacement contours, which are shown here, indicate that the maximum final deflection occurs just about or just below the mid height of the wall. So here's the exposed portion of the wall, and that would be below mid height. And again, that's confirmed by the coordinate of the maximum deflection over in draw graph. So again, we can see the radiating X displacements around that point of maximum deflection. The maximum bending moments experienced by the diaphragm wall is about 860 kilonewton meters. A change in sign occurs for the bending moment profile right near the base of the excavation. So there's where the sign change occurs. Interestingly, when you look then at, let me back up and just note that the maximum X displacement was right around here, but where the sign flips on the bending moments is often where we can expect to see the maximum shear stress in the structure. And indeed, you can see here that it's about 220 kilonewtons and near the base of the excavation. It's also interesting to look at ground settlements. These types of analyses don't perfectly reflect the sequence of events in the physical reality. And so there is often some suspect behaviors, and I'll point one out here in just a moment. But according to the math of the FE method, it is what you would expect. And so we see here that the vertical displacements are the largest at some distance behind the wall. The overall displacement pattern is downward towards the excavation, causing the ground surface then, you can see that it heaves. There's a little bit of heave. This is the suspicious part near the portion of ground right up close to the wall. And that is primarily because the top of the wall rotates counterclockwise back into the soil profile, causing a little bit of heave. So that aside, you can see here that the maximum amount of settlement is around 4 centimeters at about, right in the middle of this contour. And so we can conclude then by noting that the parametrization procedure for the soft soil model was provided in 5 rather straightforward steps. The results from multiple drain triaxial tests were required to parameterize the soft model, an important point to keep in mind when setting up laboratory programs. The material constants were then used in numerical simulations of the lab tests that produced results that compared favorably with both laboratory data and analytical solutions. I do realize, of course, that the word favorable is rather loose. You could, of course, calculate some sort of parameter to characterize the error. We used more of a visual look at the data, and I think you would agree that tests 1 and 3 were well represented, but 2 was a bit suspicious, likely because of the lab data itself. And then lastly, as an application of the soft soil model, we looked at a field example involving excavation, and we picked that out specifically to highlight that you can model submerged excavations by giving consideration to how Sigma treats the removal of a material and the need to put the water back into the excavation. For our references, I want to acknowledge the Palaxis Connect Edition version 21 Material Models Manual, as that is from where we extracted most information about the theoretical underpinnings of the model that were then used to implement it in Sigma W. And then also the book Static Stress Strain Modeling, which I've mentioned numerous times, that can be obtained from our website. And please recall that both the triaxial test simulations and the full-scale excavation simulation can be downloaded from the website, along with a PDF describing the definition of the model, the interpretation of that, and how the parameterization is done. So with that, we've reached the end of the webinar. A recording of this webinar will be available online. Please take the time to complete the short survey that appears on your screen so that we know what types of webinars are of interest to you. Thank you very much for joining us.